Okay? For example, OF2, if you look at your table, and hopefully you've already drawn this Lewis structure. All right, is this a symmetric shape or asymmetric shape? Because there are lone pairs of electrons on the oxygen atom, it is asymmetric. And because it's asymmetric, this is a polar molecule. Okay? If I drop down to BCl3, look at the Lewis structure. Okay? This has polar bonds, which is already indicated by the type of bond, but boron is bonded to chlorine. Okay? The atoms coming off are all the same. There are no lone pairs on the central atom. Now, a lot of people will say this is an asymmetric structure. They will say that it's asymmetric because there are 3 atoms coming off it. The number of atoms coming off are not important. What's important is, are the atoms coming off the same? Yes, they are the same. There are no lone pairs. This is a symmetric structure. If it's symmetric, then it is nonpolar. Okay? And that's how you're going to do it. All you have to do now for your homework is do pages 2, 3, and 4 and simply put polar or nonpolar based on looking at the molecule and determining if it's symmetric or asymmetric. Okay? Sodium chloride was ionic. If it's an ionic structure, this does not apply because we're looking at molecules, and ionic compounds are not molecules. So anything that's ionic, sodium oxide as well, none of this stuff that we've talked about the last 2 lectures apply to it. I just wanted to review how to draw Lewis structures for ionic compounds, but these will not be testable topics when it comes to the test because we're looking at the geometric shape of molecules and polarity of molecules. To be a molecule means we have a covalent bond, and that's what this unit is going to cover. All right, so that's it. You're just going to put down polar, nonpolar for all the compounds that are bonded covalently. Look at the shape of it, and later on this week and next week I'll go over some of the tables with you guys, some example problems, just to see if there's any misconceptions out there to start getting you prepared for the test, which is going to be coming up in a couple of weeks. Again, thanks for listening. All right, the last major concept in covalent bonding is looking at something called molecular polarity. Now, we've already done something which is called bond polarity. In bond polarity, we are looking at each individual bond in a chemical compound. And if it's a covalent bond, that bond can either be polar or nonpolar. Again, to have a polar bond, you are looking at 2 different nonmetals. Okay, if they're 2 different nonmetals, it's a polar bond. If it's a nonpolar bond, then it's the same nonmetal bonded to itself. Most of the compounds you're going to look at in this class are going to be over 90-95% of the molecules you're going to look at are going to be polar bonds because you're looking at a bond that forms between 2 different elements. Nonpolar is pretty simple to identify because typically nonpolar, again, it's the same element bond to itself. So here we're looking at the molecule methane. Methane is the molecule CH4. If I look at each bond, CH4's got 4 bonds and they're all exactly the same. It's a bond that's formed between carbon and hydrogen, a single covalent bond. And this bond is classified as polar because carbon and hydrogen are 2 different nonmetals. This is a polar bond because carbon and hydrogen do not share the electrons equally, and therefore it's a polar bond. A nonpolar bond is where they do share the electrons equally. An example that would be a carbon-carbon single bond. This would be an example of a nonpolar bond because it's bonded to itself and has the same electronegativities, so they fight for the electrons exactly equally in strength. Now, that's bond polarity. Molecular polarity is more of a holistic view. We're going to look at the whole molecule, okay? Because we can actually have polar bonds in a molecule, and the molecule itself can be nonpolar, all right? Now, first of all, if a molecule is found to be polar, it has an increased attraction for itself. Molecules, neighboring molecules will attract to one another because those positive and negative poles will electrically attract to each other. And what that does, that increases the boiling points of the materials because they have greater cohesive forces. It takes more energy to boil a material, And so with covalent compounds, the higher the boiling point, that usually tells us that the substance usually is a polar molecule that has strong cohesive forces within itself. An easy molecule to look at that would be the molecule HCl. In the molecule HCl, chlorine is more electronegative than hydrogen, and the reason we know that is whichever element is closest to F is more electronegative. So these two electrons are not shared equally, and what happens now is the electrons are pulled towards the chlorine, the more electronegative element, and that causes this end of the molecule to develop a negative partial charge. And this little symbolization of this little sigma negative, this stands for a partial negative charge. And sigma positive would be partial positive. So it's not a full positive and negative. That would then indicate an ionic bond. But here, because the electrical attraction is not equal, we end up having a partial positive and partial negative side. So think of it not as a total negative one, a negative positive one, but more of like a 0.5 or 0.4, a fraction of a positive and negative charge. Now, even though it's a fraction particle, it's still negative and positive. So when I have multiple HCl molecules that come close to each other, if they do so where the hydrogen and chlorine end up being in close proximity to each other, there's attraction. And this attraction is called an intermolecular force. And this is something that we will talk more about later on in the year. But the stronger these intermolecular forces are, these attractions between molecules, and this occurs for polar molecules, the stronger that attraction, the higher the boiling points and some other properties we'll investigate in these chemical compounds. Okay? This is called a dipole. A dipole is a chemical compound that has two poles. A dipole, two poles. A dipole is where the molecule has a positive end and a negative end. Okay? Now, to have a molecule that is polar, two criteria have to be met. First of all, the bonds have to be polar. You cannot have a polar molecule if it doesn't have polar bonds. So the first thing you need to be able to do is identify, does it have polar bonds? Is the bonding between two different nonmetals? If so, they have polar bonds, which, as I said, 90-95% of the compounds you're going to look at are going to meet this criteria. The second thing is the shape of the molecule is critical. The molecule must have an asymmetric shape. If it does not have an asymmetric shape, it is not going to be polar. Okay? To be asymmetric means that it will be a polar molecule. So in order for a molecule to be polar, it has to have polar bonds, and the shape of it has to be asymmetric so that the molecule overall is polar. All right? I'm going to turn the pages to a blank page to show you an example. So, CH3Cl. Real quickly, draw the Lewis structure and figure out and ask the question, is this a polar molecule or nonpolar molecule? Pause the lecture now and go ahead and do it. All right, if you've paused it and you draw the Lewis structure, this is what you get. First of all, do we have polar bonds? And the answer is yes, we do, because they're different nonmetals. Secondly, is this an asymmetric structure? And the answer is yes. It's asymmetric because one of the atoms coming off is chlorine. They are not all the same atoms. And because all of the atoms are not the same, this is an asymmetric shape. And because it's asymmetric, this is a polar molecule. If all of the atoms coming off would have been all Cl's or all H's, then it would be a nonpolar molecule because then it would be symmetric. Okay? So in review, if the bonds are nonpolar, the shape, it does not matter. If the bonds are nonpolar, there are no dipoles to worry about canceling out, and the molecule is nonpolar. Great examples of this would be oxygen, gas, nitrogen, gas, hydrogen gas. Pretty much the diatomic molecules. Anything that's bonded to itself, the bonds are nonpolar, and therefore the molecule is unpolar. If the bonds are polar and the shape is symmetric, If the atoms coming off are all the same and there are no lone pairs on the central atom, it's symmetric and the molecule is nonpolar. If, however, the bond is polar and the shape is asymmetric, now the molecule is polar. Okay, and again, here's the key thing. Symmetry, there are no lone pairs on the central atom, and all the atoms coming off the central atom are identical. Okay, so now that's what you need to do back and go back to your tables. So we just started looking at the molecule CH4. What determines asymmetry? What causes it to be an asymmetric molecule? Now, first of all, I know that the carbon-hydrogen bond is polar. So the first criteria is met. The next criteria is shape. Okay, is it asymmetric or not? To be asymmetric, first of all, the molecule must have different adjacent atoms. So the atoms that are coming off the central atom have to be different. Here, if I look at it, each atom coming off the carbon is exactly identical. So this criteria is not met. Okay, this is actually a symmetric shape because all of the atoms coming off the carbon are exactly the same. The second thing that can indicate asymmetry is lone pairs. It must have a lone pair of electrons on the central atom. Okay, so I'm going to put an or here between these two. A molecule will be asymmetric if it has different atoms coming off of it, or the central atom has got a lone pair of electrons, at least one pair of lone pairs. In both cases, there are no lone pairs around the carbon, and all the atoms coming off are exactly the same. This is a symmetric shape. And because it's symmetric, that means that the overall molecule is nonpolar. It's nonpolar because symmetric shape. Why is that? Well, between carbon and hydrogen, carbon is a little bit more electronegative. So the electrons in each bond are going to be pulled towards the carbon. Well, if we look at these little arrows, the arrow left and arrow right, they are exactly the same strength because they're between the same elements. And because they are, one's left, one right, they cancel each other out. In essence, they nullify each other. The same thing as the top and bottom ones cancel out. So we are left with what's called no result vector. And this is something that you'll talk more about in honors or algebra 2, where you sum vectors, which are arrows. And if you've done it already, you now kind of see how this is applied to this class. But in generality, what it means is if you have a symmetric shape, all of these dipoles, all of these bonds cancel each other out because of the symmetry of the molecule. If it's asymmetric, the arrows don't cancel each other and the molecule ends up being a polar molecule. Let's look at another example. Let's look at water. Okay, first of all, we have O bonded to H. Is this a polar bond or a nonpolar bond? They're different, so immediately it's a polar bond. So good, we're good there. Now we're going to look at the shape. Is the shape asymmetric? Are the atoms coming off the oxygen the same? Or are they different? They're the same. So that's not good. Second criteria, have lone pairs coming off the central atom. Oxygen does have lone pairs coming off. Since oxygen has lone pairs of electrons coming off of it, it is asymmetric. And because it's asymmetric, now these dipoles don't cancel each other out and the molecule is polar. Okay? So a molecule is polar if its polar bonds are not canceled out by being asymmetric. And that happens one of two ways. Either the atoms coming off are different or the central atom has lone pairs. It only takes one of these two. It doesn't have to be both. If one of these two criteria is met, it's asymmetric and the molecule is polar. So water is polar because of that. Now, if I look at the molecule, this is the 2D structure. the 2D Lewis structure, you would predict that the molecule probably be nonpolar, but that's not what it looks like in real life. In real life, we draw the molecule in this bent configuration, and if I look at it, oxygen is more electronegative than hydrogen. These two vectors, you'll notice, are not head-to-head vectors. They do not cancel each other out. They are both pointing towards the oxygen, and because of that, because they're not head-on, they will not kill each other. In essence, if you look at vector addition, these vectors actually add up this way. And what that means is the oxygen part of the molecule is negative and the hydrogen part of the molecule is positive. So water does have polarity because the arrows are not head-on and cancel each other out. Okay?